Excellent. Hello. So we're back talking about binary search trees, and this video is an implementation of the breadth first search algorithm. So it continues on from our code. As you can see briefly here, we did depth first search last time. Not that you have to do it first. They're related and they're very similar algorithms, but you don't have to do one before the other. So what is breadth first search? Well, breadth first search is returning all of the items in a tree in a level at a time from left to right. So a binary tree is, as you know, starts at a root and goes down nodes. You might have a left or a right child, and that continues on down. Those are called levels, right? And it has some amount of depth, and we want to return the values starting at the top at the root, return each level at a time from left to right in the tree. All right, so basically return the node's value and then return the node's children's value, and then return all of the values for all those children and all of the children's values and great-grandchildren, great-great-grandchildren, and so on. Okay, so let's write this up a bit. Let's say return node values starting at the root a level at a time and left to right. Okay, so let's stub out some stuff. We have our normal define match, right? We're going to use define match, binary search tree for breadth first search, and it takes a tree, right? So fantastic. So as usual, like we talked about in depth first search, you need your end case. Our end case is, as usual, an empty tree. And what do you do when you're empty? You very often return the empty tree. In this case, it is a list. All right? So we have our standard implementation. Then we also have our standard. We're going to match whatever, any tree, right? We don't need to save it. We don't need to pattern match on it. We're not going to pull anything out of it. And the key now is, what are we going to do at each point? What is the algorithm? So if we implement the algorithm, right, the algorithm is something to the effect of get the, let's see, what do we have? We have BTS value. If you remember from the very beginning, we created a function to get us the value out of a tree. All right. So we're going to ask for the tree's, the node's value, right? And we need to return that, and then we need to get the children for the tree, and we then need to recurse down for, we want to return the value for each tree, so we want to recurse down our breadth first search tree, right? A child for all of, all of the children, the 2 children that this node may have, or the 1, or potentially even the none, right? So what do we want to do when we get those? As usual, just like depth first, we want to append them together, right? So we're going to append these together. Now, this isn't really valid, basically, right? We have a value, but it's not a list, so append is not going to work there, right? So we'd have to turn that into the list, and this is really appending it to child or subtrees, right? And we actually ultimately need to get their values by calling breadth first search recursively. So if we start sort of there, right? Breadth first search, whoops, binary search tree, breadth first search, we're going to recurse down with the children, and for this value, we're going to need to turn it into a list. All right. So in Racket, they use let expressions to define bindings. So let's rework some of this stuff with a let expression. So we have a let expression, and what do we want to do in that let expression? We essentially want to do this append thing. And we're going to pull out these values. All right, so the first one we want to pull out is the value from the tree. The tree's value, which we do, and we have it as a list because ultimately you're going to append it. So even though it's a list and we're calling it value, that's because working through this problem, you're going to have to go with me on this, and ultimately you'll see the algorithm is basically as simple as depth first search. And then we need to get the children out of the tree, so let's grab these. All right, so now we have the children of the tree, okay? And so then we want a breadth first search on the children, okay? So we could test this out, or we can talk it through, right? But the short version is we want very similar to the, in fact, it looks almost identical to the, it's very similar to the depth first search by appending a list which in this case starts with the current node's value and then all of its children's value. All right? So, so that's excellent. And what will happen here if we run this? Well, this value on line 71 is a list, so that's good. And we're going to call breadth first search with children, meaning the two subtrees. But we've already defined our breadth first search to just take a single tree. So the algorithm, this is where the algorithm differs in a small way, but a very cool way that makes it different from the depth first search. And breadth first search should be thought of as working on a list of trees. All right, so we're going to send children. So now we're going to tear everything, not tear it up, but we're going to change things. So now we may take a list of trees. All right, so if we take a list of trees, right, we can't run BTS value on trees because it's a list of trees. What do we do when we have a list of items and we want to do something across it? We run a map, right? So now we're going to map across this thing. So now what we've done is we've taken all of our trees and we've asked for the values, right? And now we have all the values. How nice. Excellent, right? So we have all the values for it. We also now have trees here, right? So we can't just ask for the children. We need to map across it. And we get the children, but when we map across numerous trees and ask for all of their children, we're going to get multiple children for each of the subtrees, all of the trees. So let's call these children's. All right? So now we have our children's. Because this map returns a list, right, for these trees, we don't want it will return, for each tree we return a list of children. We don't want embedded lists. We don't want lists with depths. We want a single list with all of the children for all of the trees in one list. Fortunately, all that means is we need to do an append map. Every time we map, every list we get back, we append them together. And the result then is a single flat list of all of the children. Okay? So now we can append the values for the trees that were given. That's how we get every value for a row, a level, and then we iterate, we recurse down for all of the children, meaning all of the children's, which are all the children for all of the trees that we have called this function with. Okay? Does that make sense? I'm going to pause here for a second. Okay, so let's run this. Right? Let's see if we got what we wanted. So we do our printf. We breadth first search, format, wrong slash, and then we have binary search tree, breadth first search, and remember, this is different than depth first. We don't give it the tree. Well, we do. We give it the tree, but as a list, because breadth first search is imagining it's running on a list of nodes at each of the levels. And the very first level only has one node, which is the root, which in this case is the tree. And we're operating on tree 2, right? Okay, so let's run this. It's not actually going to work, but let's see what happens. So it breaks. There's a list that has too few elements. We tried to do second on it, and we tried to do it on a list that is empty. So what is second? Well, if we look back up, I'm not going to scroll back up, but when we ask for the value out of a tree, out of a node, that was in the second element, because a node is a list of 3 elements, the first being the left subtree, the second element being the value, and the third being the right subtree. So we tried to ask for the value of an empty tree. Well, why didn't this get caught on line 68? Well, it's because trees was not itself just an empty list. What must have happened is inside of trees somewhere is an empty list. So we need, how are we going to solve this? We need to throw out our empty trees because we don't want to recurse down them. There's nothing to recurse down, right? So at any level, at any point, because it's not a complete tree, there may be empty subtrees that are in that level. So if you think of that level, however down deep, some of the subtrees will be empty and some of the subtrees will have nodes that have a value and then subtrees themselves. We need to remove the empty trees at that level. So we'll do that with a filter not, right? In other words, what do we want to filter out, right? What do we want to throw out? And we want anything that's a binary search tree that's empty. We want to throw them out where? From trees. All right, so perfect. So let's run this. Still too few elements. So what happened here? Well, what happened is this trees is blue underlined because it's never being used. And this is a little bit of racketism. That's because the let value we use doesn't allow rebinding, to use rebinded variables from previous bindings. So basically, in this let on line 72, we use the previous definition of trees, not our rebound one. That's why this is with the blue underline. So to do that, we need the let star formulation, and let's run this and see what happens. Boom. We have an answer. Let's see if it's right. We have a shuffled list of 1, 0, 3, 2, 4. All right. The first one comes in as a 1, right? That's the root, so we'd better see 1. Because our numbers we know are from 0 to 4, there remains only a 0 on the left side, so that's going to have to be the next one we return. And the next one that came in is a 3, so it's going to have to go on the right. And that's perfect, right? The 3 is the next one, 2 comes in, and 4 comes in. Obviously, if you remember, depth first search gives us the leftmost parent and right, so it gives us in order, essentially. Breadth first is a level of the tree at a time. So let's run a couple just because while breadth first search algorithm, as you can see, is not really too much more complicated than depth first, it's interesting to try to verify that it's working. So the first number in our shuffled list is a 2, right? So now we know in our tree it's rooted as 2. So we also now know that the 2 values on the left side are going to be 0 and 1 because we have the numbers 0 through 4, and then because 2 is exactly in the middle, we know the 3 and the 4 are going to be somewhere on the right. So this is perfect. So then the next number that came in is a 1. That means it goes to the left. The next number was a 0. That means it has to go to the left. So now actually we have 2, 1, 0 is a left leaning. We have 3 levels. So we should see them at the 3 levels. 4 comes in, and then 3. So 4 is on the 2nd level, and 3 is on the 3rd level. So our first level of the root is 2. Then we have 1, and 0 came in, but because it's less than 2, it has to go to the left. There's already a number there. 1 was already there, so we know it's either going to have to go to the left or the right of 1, but it has to go to the left. So 0 is on the 3rd level. 4, therefore, is on the 2nd level on the right, and 3 is on the 3rd level. So we get 2 first. 1 came in. Then the 0 came in, but remember that's down at the 3rd level, so we don't want it returned. 4 came in. It's the first number on the right, therefore on the 2nd level, and then the 3 came in. Let's do another one. Let's see what another one looks like. 4. So now actually we know all numbers are going to be to the left. So we're going to have 4, and then we have 3. Boom. Right? The next biggest number. So the first level has a 4, the 2nd level has a 3, so we already know we're going to have 4 and 3. The next one is a 2, the next largest number, so we're definitely left leaning. So we get 2, then the next one off of 2 is 0, so it goes to the left of 2. Perfect. That's at level 4, and 1 goes to the right of 2, or, sorry, 1 goes to the right of 0, because it's less, so it goes to the left of 2, and then to the right of 0, so it's at 5. So we have 4, 3, 2, 0, 1. All right, we'll do one more. 0, kind of a bummer. It's not a middle one. So we're going to have zeros first. 4 is at the first level, right, and then 2. So notice 4 and 2 came in, but because it's left to right, we're going to have or 0, because 0 is rooted, so is the less number. 4 is the next level, and then 2 is going to have to go to the left of that. So we have 4, and then 3 and 1 again are going to be to the left and right of 2, but because it's left to right, we return the numbers left to right, which is 1 and 0, right? Because when you're at a tree with 2 at the root, 1 goes to the left and 3 goes to 0. All right, maybe we'll do one more, just because, like I said, it's interesting and it's harder. So top number is 2, 3 comes in, it goes to the right, 1 comes in, it goes to the 11. So great. Now, even in this subtree, it's very easy to see. 2 is the first number, but the next number has to be 1 because we're left to right per level, then a 3. Then 4 comes in, and then 0 comes in. Again, left to right by levels, that means 0 is going to appear as one of the childs before 4 on level 2 is found as a child. All right? So most of the time in this algorithm, we spent talking about it, and let's go over it for one last time. Breadth first search, actually, the magic revelation you need to come to is that you are operating on all of the nodes per level. That means breadth first search takes a list of trees to operate on. So first, that list is the root node. Perfect. We then need to get all the trees that aren't empty, right? Because at any level, there could be subtrees that are empty. So we want to throw all those out. So that was easy. Then for each of those trees, we want to get the values. Because remember, that's what goes next. And then we want to get all of the children for all of those subtrees. And that's what we call breadth first search on. So if this were a complete binary tree, level 1 would have 1, level 2 would have 2, and then to the 2, so level 3 would have 4, and then there's 2 each of those, so it's 8, level 3, because it's 2 to the power of that level, because this is a binary tree. Next level is 16, 32, right? So the key to this algorithm is to realize that breadth first search it needs to operate on a list of nodes, because it's operating, as the actual words say, we need to return the values of all the nodes per level, left to right. All right, I think I've hammered that in. Good luck. Thanks. Bye.